Hello everyone, welcome to today's lecture on multiplexers, demultiplexers, encoders and decoders, an important topic in digital system design. In this video, we'll focus on the first two combinational logic circuits, multiplexers and demultiplexers. These circuits are widely used in digital communication systems, processors, memory organization, data routing and embedded systems. By the end of this session, you will understand how multiplexers select data from multiple inputs and how data multiplexers and demultiplexers distribute data to multiple outputs. We will also solve design examples and discuss practical applications that are frequently asked in university examinations. So let's begin with the concept of multiplexer. A multiplexer is one of the most important combinational circuits in digital electronics. The word multiplexer is commonly abbreviated as MUX. The main purpose of multiplexer is to select one input from many available inputs and to transfer it to a single output. Because it selects one signal among many, it is also called as a data selector. Think of it like a railway station junction. Many railway tracks come towards to the junction, but depending on the signal, only one track is connected to the outgoing track. Similarly, among several input signals, only one is connected to the output. So let's understand the structure. A multiplexer consists of three main components. First, it has n control inputs, which are also called as selection lines. Second, it has two raised to n data inputs. Finally, it has one output, only one output. The selection lines determine which input reaches the output. For example, if there is no selection line, the multiplexer can select between two inputs. If there are two select lines, it can select between four inputs. Similarly, three selection lines allow the selection of 8 inputs. This relationship is very important. Always remember the formula: number of inputs equal to raised to the power of number of select lines. This formula is frequently asked in examinations. Now let's discuss about the simplest multiplexer. This slide shows the 2:1 multiplexer. Here we have two data inputs, I0 or I0 and I1, one selection line A, one output Z. The Boolean expression is Z equal to A dash I0 plus A I1. Let's understand how it works. When the select line A is 0, its complement A dash becomes 1. Therefore, output becomes Z equal to I0. Input I0 reaches the output. Now let's consider A equals 1. A dash becomes 0. The equation becomes Z equal to I1. Now input I1 reaches the output. So depending on the selection line, either I0 or I1 appears at the output. This is the simplest example of a data selection. Now let us increase the number of inputs. This is a 4:1 multiplexer. It contains 4 inputs, 2 select lines, 1 output. The selection lines are A and B. Together they generate 4 combinations: 0, 0, 0, 1, 1, 0, 1, 1. Each combination selects one output. When AB is 0, 0, output is I0. When AB is 0, 1, output becomes I1. When AB is 1, 0, output becomes I2. When AB is 1, 1, output becomes I3. Observe the Boolean expression carefully. Each term represents one min term corresponding to one selection combination. Students should remember both the truth table and Boolean expression because they are important for university exams. Here we have an 8:1 multiplexer. Now there are 8 inputs, 3 selection lines, 1 output. The selection lines are A, B and C. Since there are 3 selection lines, the total possible combinations become 2 power 3, which equals 8. Therefore, each binary combination selects exactly one of the 8 inputs. For example, 0, 0, 0 selects I0, 0, 0, 1 selects I1, 0, 1, 0 selects I2, 0, 1, 1 selects I3, 1, 0, 0 selects I4, 1, 0, 1 selects I5, 1, 1, 0 selects I6, 1, 1, 1 selects I7. Notice that the most significant bit and the least significant bit are indicated in the slide. Students often make mistakes while identifying MSB and LSB. Always read the truth table carefully before writing the Boolean expression. This figure represents the standard symbol of a multiplexer. Instead of drawing all Boolean gates individually, engineers usually represent the circuit using this compact symbol. The selection inputs are connected on one side, multiple data inputs are connected on another side, and only one output is obtained. Using standard symbols make large digital circuits much easier to understand and design. Now let's discuss this design problem. Suppose only 4:1 and 2:1 multiplexers are available. Can we build an 8:1 multiplexer? That is our question. The answer is yes. We first divide the 8 inputs into 2 groups. Each group is connected to one 4:1 multiplexer. The outputs of these 2 multiplexers are then connected to one 1:1 multiplexer. The most significant selection line decides which 4:1 multiplexer output is selected. This concept is called cascading multiplexers. This is another important design problem. To build a 16:1 multiplexer, we need to design a 16:1 multiplexer. So we need multiple 4:1 multiplexers arranged in different stages. In first stage, 4 multiplexers reduce 16 inputs to 4 outputs. In second stage, one more 4:1 multiplexer selects one amongst those 4 outputs. This hierarchical approach simplifies complex circuit design. Questions based on cascading multiplexer are frequently asked in semester examinations. One practical application of multiplexers is the multiplexer bus or bus multiplexer. A bus consists of multiple wires carrying binary data between different components. Instead of providing separate connections for every device, a multiplexer selects which device can send data through the common bus. This reduces wiring complexity, saves hardware, and improves system organization. Bus multiplexers are widely used in processors, microcontrollers, and communication systems. So far we have seen how a multiplexer selects one input from many. Now we move to the opposite operation called the demultiplexer. A demultiplexer receives one input and distributes it to the one of many outputs. Because of this, it is called as a data distributor. A demultiplexer contains one data input, n selection lines, and 2 raised to n outputs. Depending on the selection lines, the input transferred to the one selected outputs, while all remaining outputs stay at 0. Now, notice that how this operation is exactly opposite to a multiplexer. A multiplexer has many inputs and one output. A demultiplexer has one input and many outputs. Remember this comparison as it is commonly asked in Viva examinations. This example shows a 1 to 4 demultiplexer. There is one input and 2 selection lines and 4 outputs. If the select lines are 0, 0, the input reaches output W. If they are 0, 1, the input reaches output X. If they are 1, 0, the input reaches output Y. If they are 1, 1, the input reaches output 0. The Boolean equations shown on this slide describe each output mathematically, and only one output becomes active at any instant, depending on the selection lines. Next is decoder. So that we will discuss in the next lecture. Let's summarize today's lecture. We learned that a multiplexer is a data selector. It selects one input from multiple inputs using selection lines. We studied 2 to 1, 4 to 1, and 8 to 1 multiplexer, their truth tables, Boolean expressions, and cascading techniques. We also discussed bus multiplexers and their practical applications. Next, we learned about the demultiplexer, which performs the opposite operation. A demultiplexer distributes one input to one selected output. Understanding these concepts is essential before learning decoders and encoders. In next video, we will study decoders and encoders, including active high, active low decoders, enables input priority encoders, and their practical applications.